Hi, everyone. First of all, thanks to the organizers for the nice conference. It's a pleasure to be here. My name is Shishir Khandelwal. I'm at Lund University. I'm a postdoc in the group of Armin Tavakoli. So today I'll be talking about some simple but surprising results that we had last year on generating maximal entanglement in autonomous quantum thermal machines. So first of all, what are autonomous quantum thermal machines? They're just setups that utilize incoherent interactions of thermal reservoirs with the system to produce some useful output. So this output can be work, cooling, thermoelectricity. It could also be something entirely non-classical, such as quantum entanglement. So what makes these machines autonomous for me is the lack of external control and time-independent interactions, also lack of source of coherence while the machine is operating. So to me, there are three main reasons to investigate such systems. First of all, in the lack of external classical control, you can aim to explore what is truly quantum in a quantum thermal machine. Secondly, because the machine operates only with the thermodynamic exchange from thermal reservoirs, you can quantify the resources needed for its operation in terms of heat and energy exchange with the reservoirs. And thirdly, and this is a practical reason, so thermodynamic cost of classical control is typically very high, which means that we would typically like to avoid it. For more details, I would recommend looking at this nice review. So let me now come to the problem at hand. So I have here, the problem is you're given an arbitrary quantum state, or more specifically a separable quantum state, and you would like to generate a steady state that is entangled using only thermal interactions and in an autonomous way. So this is a question that, at least to my knowledge, people have considered for about 20 years now. The answer is already known. It's indeed possible to create entanglement in such setups. But there are many recent questions that people have tried to answer. For example, how much entanglement can you generate in such scenarios? Secondly, can you generate entanglement beyond bipartite systems and also beyond qubit systems? For example, these two works. And lastly, and importantly, is the generated entanglement actually useful for anything? So does it have an operational non-classical meaning to it? So let me now give you a very simple but informative example of an entanglement machine. So here I have two qubits coupled to two thermal reservoirs. Here I'm taking fermionic reservoirs. The Hamiltonian of the system is given by this simple expression. And I'm assuming weak coupling between the system and reservoir, and also weak coupling between the qubits. And in this situation, you can express the dynamics of the system in this local Lindblad form, in which these dissipation terms enter locally with the qubits. So here, the dissipators are the usual Lindblad form, and the rates are determined by the statistics of the reservoir. And it is indeed known that steady-state entanglement is possible, in fact, for a wide range of parameters. For example, in this work from 10 years ago. And it's also known that there's a minimum current that you require in the steady state to see entanglement. So this is an if and only if condition, where this is C represents here the concurrence. So it really is the thermodynamic exchange with the reservoirs that drives entanglement production in this scenario. But the problem with this model is that the generated entanglement is typically very weak. It's too weak to be useful for anything. So naturally, people have considered many different ideas for minimal resources that you can add to the setup, both autonomous and non-autonomous, to boost entanglement production. So for example, I said that it's thermodynamic exchange that drives entanglement production. You can imagine that population inversion on one of the reservoirs can give you more entanglement. Also, for example, repulsive interaction, which eliminates doubly occupied subspace, it can boost entanglement even further. And there are also non-autonomous means, such as feedback mechanisms and heralding, which may, which are not only autonomous, but in the case of heralding, also non-deterministic. Even though none of these examples and many, many others don't go beyond a certain level of entanglement, not close to maximal entanglement, it's known that you can have operational non-classicality in this setup. But what people have not really answered is how much entanglement can you create in the steady state? Can you specifically create maximal entanglement? So to answer this question, it's whether you can create a pure and maximally entangled state in the steady state, it's useful to go back to some basics. So first of all, note that Lindbladian evolution is usually has a mixing effect, which means that if I have an initially pure state and it undergoes some Lindbladian evolution, it will evolve into a mixed state. But exceptionally, if a pure state has to be the steady state of our Lindbladian, it can be shown that there are only two conditions that need to be satisfied. First of all, that the dissipators of the Lindblad equation must annihilate this pure state. And secondly, the state must be an eigenstate of the Hamiltonian. And the proof of this can be found in this paper from 2008. So first of all, note that the Hamiltonian that I showed you for the two-qubit system has two Bell states as eigenstates. So all one has to do is construct a set of dissipators that annihilates this one of these states. And it can be shown, and you can convince yourself with a short calculation that this is the only set of dissipators in the local picture, so in the computational basis, that has this property of annihilating, of being annihilated by these dissipators. The problem now is that this equation does not have a unique steady state. It has two zero eigenvalues. So what we've shown is that the two-qubit setup actually cannot produce a unique steady Bell state. So this motivated us to look at the minimal extension to this two-qubit model. So the natural thing is to add one extra qubit. So here I have a three-qubit system. The first one is coupled to a reservoir at non-zero chemical potential. The second one is decoupled from any thermal reservoir. And the third one is coupled to a reservoir at zero chemical potential. In addition, you'll see that I have flip-flop interactions between qubits 1 and 3 and qubits 2 and 3, while all three qubits are also interacting via some repulsion, Coulomb-like repulsion term. Here I take the ideal limit. So I take a very large Coulomb repulsion, a very large chemical potential, while maintaining that the Coulomb repulsion is much larger than the chemical potential. This may seem rather manufactured and unrealistic, but this is the mathematical condition that we need to reach the state exactly. Actually, the scheme works very well beyond it as well. So first of all, a large Coulomb repulsion will ensure that double occupation does not happen in the state. And a large chemical potential ensures that, that this reservoir can only provide excitations to the system. It can never gain anything from the system. This also means that the right reservoir will only be, will be the only exit way for excitations from this three-qubit setup. And the last condition is basically just needed to ensure that there is no double excitation at any point and under any circumstances in the evolution of the system. So beyond this, this ideal limit, you can take arbitrary couplings and arbitrary system reservoir couplings as well, and arbitrary temperatures, as long as you remain within the validity of this Lindblad equation. So without getting into too much detail, most of which you can find in this nice paper from 2021, you will find that when you apply this ideal limit, only three dissipators matter, these three in particular. And now that we have our Lindblad equation, we can find its steady state. It happens to be given by this expression. And with a simple parametrization of theta, you can see that this is just a partially entangled state of two qubits along with the ground state of the third qubit. So what we find is that for any parameter regime of the couplings, the steady state is pure and partially entangled. as long as you are in the ideal limit. This, as expected, and as I said before, this has to be an eigenstate of the Hamiltonian, which is what we find. And lastly, when you take these couplings G23 and G13 to be equal, you find that you have a perfect singlet steady state. So what we find now is that what was impossible with the 2-qubit setup, a third qubit has actually allowed the generation of maximal entanglement in the setup. And this is despite the fact that the third qubit is not entangled at all. It's just always pushed into the ground state. So one can understand this, this result further by taking some inspiration from atomic physics. So let's say I start in the ground state of 3 qubits. So one possibility is that I gain an excitation from this reservoir and go to the state 100. The other possibility is that I gain an excitation from this reservoir and go to the state 001. These two states are now coupled with this interqubit interaction. And there's a third state that is coupled through this interqubit interaction. And in the end, what we're finding is a coherent superposition of these two states. And for those of you with an atomic physics background, you will see a connection with lambda systems here. And what we're finding is that there's a direct analogy with coherent population trapping. For those of you who don't know this, you should look up dark states on Wikipedia, and you'll find this expression. So in the end, what we found is that what this is actually is the solution of the Schrödinger equation of the effective 3-state model when you disregard dissipation entirely. And because this qubit is always depopulated, this means that in the steady state, it can provide no excitations to the right reservoir. And this means that there cannot be any current, despite the fact that the reservoirs are heavily out of equilibrium. So this is what is known as dark or a non-conducting steady state. So now that we have, how much time do I have? Okay, I have time, right? So now that we have a clear picture of how to create maximal entanglement in 2 qubits, we can ask the question whether we can produce genuine multipartite entanglement. So let me remind you, we saw in a previous talk, this genuine multipartite entanglement basically means that the state cannot be written in this biseparable decomposition. It's already known that it's possible to generate GME in such setups, but there are 3 important problems. First of all, you need a heralding procedure, which means that you need to perform local filtering measurements and then post-select on the outcomes. This post-selection also means that this result is non-deterministic. Even though you can produce a large amount of entanglement, there's a near zero probability of reaching the target state, which is maximal entanglement. And lastly, and very importantly, you need global interactions, which means that they're not just slightly harder to handle theoretically, they're also much harder to create experimentally. So now we ask the conceptual question, are local pairwise interactions sufficient to generate GME deterministically, so with probability 1? So for this, we can make a naive attempt, just adding another qubit to be entangled in our setup. But this actually does not lead to a GME. This does not lead to a unique steady state at all. But instead, if you add another one of these qubits another one of these sync qubits coupled to a reservoir at 0 chemical potential, you will find that, basically an extra triangle of interactions here, you will find that qubits 1, 2, and 3 are entangled, while these 2 blue ones are pushed into their ground state. And in the end, we will find, if these couplings are equal, that we have a W state of 3 qubits and ground state of 2 of these blue qubits. And now we can push it further. We can have an n qubit generalization. So we have this machine that creates an entanglement between 3 qubits. We can just make a bigger setup. And for every additional qubit that we want to entangle, we add another one of these sync qubits coupled to a reservoir 0 chemical potential, another one of these triangles. And what we'll find is that we have entanglement between qubits 1 to n. And for each additional qubit that we want to entangle, we again have 1 extra sync qubit. So the total number of qubits is 2n minus 1. And apart from this, we can have arbitrary system reservoir couplings and temperatures within the validity of the Lindblad equation. And we will find that we have a W state of n qubits. And again, this I'm not going into too much details, but if we take unequal interqubit couplings, we will obtain partially entangled W-like states here. So with this, I would like to conclude. So the smaller, we've shown that the smallest thermal machine that can generate a Bell state as a steady state of its evolution consists of 3 qubits. We also answered the very nice conceptual question whether thermal resources and pairwise interactions can generate the strongest forms of multipartite entanglement. And something that we didn't really talk about is G at Z states. So I had Coulomb interaction in my setup, which will definitely not be useful for generating G at Z states. We also didn't talk about high dimensional entanglement. And I also didn't talk about non-autonomous means of producing entanglement. Since there's a lot of interest at this conference in non-Hermitian physics, I would like to say that there is in fact a way to produce Bell states with some non-Hermitian effects. For more details, I would refer you to this paper. Thank you very much. I'm happy to take any questions.
Thanks, Shishir, for the nice talk. Do you have a question for Shishir? Yes.
This is from a practical point of view. How do you realize sinks in experiments?
So I don't know what the general idea would be, but I've been told by experimentalists in quantum dots that they do it, because the sink idea is actually quite simple. It doesn't have to be zero chemical potential per se. What you have to have is a very large chemical potential on one of the reservoirs. As long as you have this, you don't actually care about what happens here. It can be arbitrary temperature. It can also be non-zero chemical potential, as long as it's not too large.
So you don't really need a bias of temperatures to do this, right?
No, you don't.
Okay. So another thing, can you once more explain that you said something about even if you have bias of temperatures, you don't have currents or something?
Yeah, exactly. So let me go back. So the idea is basically this: because this qubit is depopulated, it cannot transfer any excitations here.
So which 2 qubits are getting, the singlet is between which 2 qubits?
It's between the gray ones, I should have mentioned.
Okay.
It's 1 and 2.
Okay, thank you.
While number 3 is depopulated.
Okay, thank you.
Yeah, hi Shishir. So can you just walk us through again the physics of the limit that you took in the U over G going to infinity?
Sure.
And could you also comment what happens if you just back off of that limit?
Yeah, I can show you a plot if you want, but I can repeat myself with this limit. So the idea is basically this: when you have a large chemical potential here, you're just creating a reservoir that can only provide excitations into your system. It can, if you just calculate the rates with fermionic statistics here, it's easy to see. This thing is necessary to ensure that that you prevent double occupation, because in the end you want a singlet state, so you don't want double occupation in the setup. And the last one is slightly more technical. It kind of arises when you look at the rates exactly, and it turns out that it's necessary.
So if you go to kind of spin qubit architectures right now, I guess you could take mu to as large a number as you, I mean, you could design this, but could you spin polarize the leads instead? Like, is that a possible solution out of your T going, like, essentially if you spin polarize the leads by, that's one way to kind of only make sure that electrons flow one way by using Pauli exclusion.
I suppose that could be a way. We never really looked at spin polarization or actually spin qubits. We looked at quantum dots mostly. And in quantum dots, it's just that you have to provide a bias voltage here. at this.
Yeah, but if you look at the occupancy with like some finite U models, it's the same. It's just you have to also, poly will allow you to double occupy the states, right? That's what you're trying to avoid anyway. So is this, I mean, and what, so you said that there's a plot. Could you just say
Sure.
what happens to the entanglement without maybe, oh, the plot's right here, okay.
I have to, or maybe yeah. So on the left, you see a plot of the, of the concurrence with the chemical potential and the Coulomb repulsion. And here you really see that as long as, actually this is not a good scale, it should be temperature here. Just imagine that it's temperature. As long as the Coulomb repulsion is high and the chemical potential is high, while maintaining that this is higher than this, you have almost perfect entanglement. You don't have to actually go to infinity.
And are those realistic numbers? Like U is 15 and
So
let's say mu is 6?
For this, we've checked with quantum dots. It's realistic for quantum dots.
Okay.
Actually, quantum dots are quite natural for this because there's well, electrons have natural Coulomb repulsion. You don't have to engineer.
Thank you.
Thanks. Okay, do you have any other question? It seems no. So let's thanks, Shishir once again for the nice talk. And we